Welcome to the Explainer, Grade 10. Today we're tackling one of the absolute most fundamental rules in all of chemistry, the law of conservation of mass. If you've ever looked at the world around you and wondered how things change, break down, or rebuild, well, you're in exactly the right place. We're going to put on our detective hats today and carefully track down some microscopic secrets of the universe. Let's get right into it. So to kick things off, picture a campfire. You toss a massive, heavy log of wood right into the flames, right? It burns intensely for hours. But when you come back the next morning, that huge piece of wood is just gone. It leaves behind this tiny, lightweight pile of ash. So here's a question for you. Where did all that mass go? Did the heavy wood just literally vanish into thin air? It's actually a super common misconception to think matter can just be destroyed. But as you'll see, science tells a totally different and honestly way more fascinating story.
Here's our roadmap for this explainer. We'll start with the burning wood mystery, move on to the law of conservation, talk about rearranging the atoms, tackle the atom counting challenge, and finish up with real-life chemical reactions. Okay, let's dive straight into part 1, the burning wood mystery.
When that heavy log burns, it really does look like it vanishes. But actually, it doesn't. It's just transforming into entirely different forms. Sure, you see the ash left behind, but what you might not be thinking about is all the smoke, the invisible gases like carbon dioxide, and even the water vapor that escaped into the air during the fire. Think about it. If you could somehow trap all of those invisible gases and the smoke in a giant invisible balloon, you'd realize something incredible. The matter didn't leave the universe. It just put on a new disguise and floated away.
What we're witnessing with that fire is a perfect example of a chemical reaction. This is basically a process where new substances are formed. The chemical bonds of the original material break apart and new bonds form, changing the materials into something entirely new. So the wood isn't just getting smaller or fading out of existence, it's chemically reacting with oxygen in the air to become ash, smoke, and gas. Moving right along to part 2, the law of conservation.
You know, this mystery of the vanishing wood isn't exactly a new question. It was actually solved way back in the 18th century by a brilliant scientist named Antoine Lavoisier. He's widely known as the father of modern chemistry. And Lavoisier is famous for establishing this incredible principle, the law of conservation of mass. What this means, simply put, is that matter cannot be created or destroyed during an ordinary chemical reaction. Basically, the total amount of matter, or mass, that you start a reaction with has to be exactly equal to the mass you end with. It is an absolutely unbreakable rule of nature.
Lavoisier summed this up perfectly. He said, "Nothing is lost, nothing is created, everything is transformed." I absolutely love the energy of that statement. It completely shifts how you view the world. So the next time you see something breaking down, just remember Lavoisier's words. The matter isn't vanishing, it's just transforming.
All right, let's look at part 3, rearranging the atoms. To truly understand this transformation, we need to zoom way in and picture how this actually happens on a microscopic level. Think of atoms exactly like building blocks. Imagine you've got a massive spaceship built out of these blocks. If you take that spaceship apart and use the exact same blocks to build, say, a castle, well, you didn't destroy any blocks, right? And you didn't magically create new ones either. You just rearranged them. That is exactly what happens during a chemical reaction. The original atoms are simply shuffled around into new combinations to create completely new substances. Now, to talk about this scientifically, there are 2 vital terms we need to memorize. On the left side of any chemical equation, we have our reactants. These are the original atoms and molecules that exist before the reaction takes place. Then, on the right side, we have our products. These are the totally new substances that exist after the reaction. But remember our building block rule. The exact atoms present in the reactants absolutely must mirror the exact atoms present in the products.
Which brings us to part 4, the atom counting challenge.
I hope you're ready because it's time to act as mass detectives. We're going to mathematically prove Lavoisier's theory using the elements that make up a molecule of water. So grab your mental calculators. Here's our specific chemical equation for the challenge. On the reactant side, we're taking 2 molecules of hydrogen gas and reacting them with 1 molecule of oxygen gas. On the product side, this perfectly produces 2 molecules of liquid water. But before we count them out, do you think the atoms will balance out perfectly? Let's find out. Let's walk through this table step by step. Hydrogen gas naturally exists in pairs, so 2 molecules of hydrogen actually means 2 times 2, which gives us exactly 4 hydrogen atoms on the reactant side. Oxygen gas also travels in pairs, so one molecule gives us two oxygen atoms. Okay, now let's look at the product side, our two molecules of water. Since each water molecule has two hydrogens and one oxygen, multiplying that by 2 gives us exactly 4 hydrogen atoms and 2 oxygen atoms in the product. Look at that. The exact same atoms we started with are what we finished with. No blocks were lost.
So, how do we translate those atoms into actual measurable mass in grams? We just follow a very deliberate 3-step process. Step 1. We check the periodic table to find the atomic mass. Hydrogen has an atomic mass of about 1.008. Step 2. Just for ease of calculation in this challenge, we round that to the nearest whole number, which is 1 gram. Oxygen is 15.999, so we round that to 16 grams. Step 3. We simply multiply those rounded masses by the number of atoms we just counted.
Let's execute that final math challenge right here. For our reactants, we had 4 atoms of hydrogen. We multiply that by 1 gram, giving us a total of 4 grams. We had 2 atoms of oxygen multiplied by 16 grams each, giving us 32 grams. Add those together, and our total reactant mass is 36 grams. Now for our product. A single molecule of water is made of 2 hydrogens and 1 oxygen, so 2 grams plus 16 grams equals 18 grams per molecule. And since our reaction created 2 molecules of water, we just multiply 18 by 2.
And there it is, 36 grams. This is a huge aha moment. We started with exactly 36 grams of hydrogen and oxygen gas reactants, and we ended up with exactly 36 grams of liquid water product. The math flawlessly proves the law of conservation of mass. All right, let's wrap things up with part 5, real-life chemical reactions. So the really crucial point here is that this isn't just some abstract theory for textbooks and lab experiments. This exact mathematical balance governs the entire world around us, every single day. Let's step out of the math and into the real world. Take a look at these everyday reactions, like when iron sits outside in the rain and reacts with oxygen to form rust, or when you mix baking soda and vinegar to create a bubbling volcano of carbon dioxide, or even when you simply light a candle and watch the wax slowly burn away. Just like our burning log of wood from the very beginning, none of these physical processes actually destroy a single ounce of matter.
If we were perfectly able to trap all the gases, all the smoke, and all the rust created in those everyday reactions, and weigh them against what we started with, the scales would be perfectly balanced. No matter how drastic the visual change is to our human eyes, on a microscopic level, the atoms are just doing a perfectly balanced dance, swapping partners and building new things without ever vanishing.
I want to leave you with a final thought to carry with you. Now that you understand the law of conservation of mass, you can honestly never look at the physical world the exact same way again. Next time you see something burn, rust, or melt, don't just see the destruction. Ask yourself, how are those tiny, invisible building blocks rearranging to form something entirely new right before your very eyes? Stay curious, keep investigating like the scientific detectives you are, and I'll catch you in the next explainer.